smooth curves. Now we're going to switch gears. We're going to continue talking about graphs, but of rational functions. That's rational means fraction. So we're looking at things with fractions in them. So, a rational function is what you get when you divide two polynomials. And we know that if we are going to divide, we can't divide by 0. So it's two polynomials and the denominator is not 0. That is a rational function. With these rational functions, today we are going to talk a lot about the domains of them. So your domain is asking for your possible values of x. You with me, Lane? Yeah. So when I ask you to find the domain, I'm asking you what x can be. Now with a polynomial, we didn't have to worry about it because polynomials keep going forever in both directions. Rational functions, though, we have a concern because if we're dividing things, what did I already say can't happen? When you have a fraction, the denominator cannot be 0. So anything that makes the bottom 0 is going to be excluded. That value of x won't work. And that's the place where our graph is going to do funny things. So the domains of these is everything except what makes the denominator 0. And that's going to be where we really need to pay attention to our graph. So let's find the domains of these. So the first one, r of x, our function is 2x squared minus 4 over x plus 5. So for the domain, I'm only going to look at the bottom. And all I care about is what would make x plus 5 equals 0. Okay, really, we know that x plus 5 can't be 0, because that would give us divided by 0. And so if I solve that, x cannot be negative 5. So my domain is telling me what x can be, and can be anything except negative 5. So I can write negative infinity to negative 5. Union negative 5 to infinity. Domain is everything else. When I look at b, so we just know denominator can't be 0. So that tells me x squared cannot be 4. When you square root plus and minus, you get the x cannot be right. This one, the interval becomes a little longer, because if you think about what it's telling us, it's saying you can have anything smaller than negative 2, anything between negative 2 and 2, or anything bigger than 2. So it actually breaks into 3 pieces. It's negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. In general, the more values that x can't be, the longer that interval becomes. My rule is, if you only have one value that x cannot be, you must write your domain in interval notation. I will allow, if it's multiple values, I will allow you to list them. So on this problem, you could tell me this is a domain, which is the answer I'd really like to see. Or on this problem, if you told me x can't be plus or minus 2, I will accept that. So just because the more values x can't be, especially if we add 3 or 4, your interval notation gets really long. So if it's more than one value, I will allow you to just tell me x cannot be these numbers. But if it's just one value, the interval isn't too bad. I want to see that. Does that seem fair to everybody? I said x cubed over x squared plus 1. Alright, so we know denominator can't be 0, so x squared plus 1 can't be 0. So x squared can't be negative 1. What happens if you square root that? When we draw graphs, can we graph eyes? No, we're only talking about real numbers. So if the only things x can't be are imaginary, what do you think our domain is? D. Negative x squared plus 2 over 3. So all we care about is the denominator. The denominator can't be 0. Does 3 ever equal 0? No. So what's my domain? So if I look at this one, denominator x minus 1 can't be 0. So x cannot be 1. So how do I want that written? I'm going to put one up here. You guys want a hard one? Okay, x plus 1 over x cubed plus 4x squared plus 3x. Your denominator can't be 0. So x cubed plus 4x squared plus 3x can't be 0. So if you take out an x, and then factor, so what can x not be?
0, -3, which I guess you don't really need the 0.
You actually, I mean, you need it on there. So those are the things x can't be. I would accept it like that because there are so many. If you tried to write the interval, it would be negative infinity to the smallest number, union that number to the next one, union that number to the next one, union 0 to infinity. So the interval is pretty long
Just gets
on that one.
inefficient.
Yes, it does. So just one value, give me the interval. More than one value, you can just list them. As long as you say x cannot equal. Don't say x does equal. Those are different things. All right, so that is the majority of your homework tonight, is practicing finding these domains. Are we okay with that? So it turns out these domains are really, really important for the graphs. And next week, we're going to actually start graphing them. But I have just a couple other slides that I want to go over. If I asked you, are these two functions equivalent? Are they the same? So I have x squared minus 1 over x minus 1 and x plus 1.
Yeah, they are, because if you divide x squared over x is x, and then negative 1 over negative 1 is 1.
Well, you can't divide them that way, but what could you do to the top? Before we're trying to solve it, we could factor that, right? Difference of squares, that factors into x plus 1, x minus 1. It has to be in factored form before you could reduce things. But then if you reduce, we get x plus 1. So they look equivalent. And in everything we've always done, we've treated those as equivalent. We would take something and reduce it. But they're actually not, because they're almost equivalent. What's the domain of this one? I told you domain is based off the original problem. What's the domain of that?
Can't be 1.
It can't be 1, so it's negative infinity to 1, union 1 to infinity. This one, it's just a line. What's the domain of that one? Right. So these are almost the same, but their domains are not. Domains are based off the original function. And it turns out that when we learn more about the graphs, they're almost the same. On this one, you just get this line. On this one, we'll learn that actually what happens is you have a line and it has a hole in the line. It's a line everywhere except you can't plug in one. So the graphs are slightly different on this. So I just put this up there to remind you, when I ask domain, it is based off that problem. Do not reduce anything. It is from the original.
So why can you not divide? Because we've done that before, where you divide all, or exponents, because you can, sometimes there's negatives and then you flip it.
That's when it's all one term, no addition or subtraction that you use those. So what we're going to talk about next week is asymptotes. So asymptotes are lines that our graph gets close to without actually touching. And there's 3 different types: horizontal, vertical, and oblique. Today, I am going to give you a couple problems where we look at pictures and find them from the picture. And then Tuesday, we'll start talking about how to find these things from the equation itself. But just a couple things, you might want to jot this down. Make sure you know the 3 types: horizontal, vertical, and oblique. We are getting close to, but not touching them. It is possible, we will see some scenarios where a graph might go through a horizontal and an oblique asymptote, but it will never cross a vertical asymptote. So those are just a few properties of these asymptotes we will be using next week. So the most basic rational function is our reciprocal function. Alright, so if I asked you to graph that, the reciprocal is 1 over x. And we know that in general, if we want to graph something and we don't know what it looks like, we make a t-chart. What number can I not plug in here? 0. It's not in the domain. We can't have 0. But I could put in like 1, 2, 3. If I put in 1, 1 over 1, 1 over 2, 1 half, 1 over 3, 1/3. 1, 1, 2, 1 half, 3, 1/3. What if I put in 1 half? What's 1 divided by 1 half? Put the 1/2 in parentheses. Remember 1 divided by 1/2. If you want to divide by fractions, you flip and multiply. So if I put in 1/2, I get out 2. What would happen if I put in 1/3? Or, sorry, if I put in 1/3, what would we get out? 3. All right. Will I ever do 1 divided by something and get 0? No. And we can't plug in 0. If I did some negatives, if I put in -1, we get -1. If I put in -2, I get. If I put in -1/2, I get -2. -1, -2, -1/2, -1/2, -2. So what these graphs look like, these are curves, and it's getting close to the x-axis, but it's not going to hit it. If I do 1 divided by something, it's getting closer to 0, but it never equals 0. Okay, with my x's, I can't plug in 0, so it's getting closer to this y-axis, but not hitting it. Same thing down here. Okay, so this is what is called the reciprocal function. The x and y axis here, those are lines we're getting close to but not touching. Those are the asymptotes. When we are graphing lines, we'll graph those as dashed lines. So we can see we're getting closer to that, but we're not actually crossing it. So when you have rational functions, you will have those asymptotes, the lines we're approaching. Let's answer just a couple questions over this. Domain, we already kind of talked about. We said x can't be 0, so how would we write that domain? We have things to the left and the right of the axis, but not on it. All right, the range. What y value do we never hit? 0. It turns out to be the same on this one. Infinity, 0, union, 0 to infinity. The vertical asymptote. An asymptote is a line, so you have to give me an equation. Vertical lines are x equals a number. What's the x value that we never touch? 0. So x equals 0 is that vertical asymptote. The horizontal. Horizontals are y equals. What's the horizontal line we don't touch? 0. And then I threw on here just to review. It's been a long time since we talked about it. Even and odd. Remember, even is the same as symmetric to the y-axis. If I fold this thing over the y-axis, does it overlap itself? No. Odd is the same as symmetric to the origin, which means you flip over the y and the x. If you make 2 flips, would it overlap? Yes, so this is an odd function. Right, so next week we will be looking at a lot more of the rational functions, but I wanted to show you one and show you what those asymptotes look like on there. Are there any questions about that? Final example. I'm going to give you a graph. And we're going to answer some questions about it. So, from this graph, can you tell me the domain? So this is coming from, this first piece is from -infinity. And it stops, what does it look like it's approaching? 2. Getting closer to 2, but it doesn't hit it. So it's -infinity to 2, union 2 to infinity. My range, what's my y value we don't touch? At 1. -infinity to 1, union 1 to infinity. Let's come down here. What's the equation of the horizontal asymptote? Y equals 1. So notice your horizontal asymptote is the value that doesn't exist in your range. What's my vertical asymptote? X equals 2. Notice the vertical asymptote is the value that doesn't exist in the domain. X and Y intercepts. Where do we cross the x-axis? Or if you told me the point, that's 1, 0. Y-intercept, where do we hit the y-axis? Gave me a point, x is 0, y is 1/2. Last thing, does this have an oblique asymptote? That's just another line that's not vertical or horizontal. Do we have one? No. So your graph doesn't have to have all the kinds, but we can see multiple asymptotes.